Welcome to Ask and Learn.
Hi, in this question, we are asked to prove that this formula for the sum of integer square are correct, and it is true for any positive integer n. And we are going to use math induction to do this. First, we let this whole statement name it p of n, and we are going to do this in two steps, right? Basic step and inductive step. So first, basic step, we just need to show that it is true for the first positive integer, which is 1 here. The statement at 1 will have left hand side as just a sum of 1 terms, right? And the right hand side will put 1 into substitute n for 1. And we're gonna get that this is 6/6, which is 1. So the statement is true for for n equal to 1. So basic step is clear. Next is inductive step. So in this step, we want to prove that if the statement is true for any n, for any positive integer n, it will force the next statement, that is p n plus 1, to be true as well. So p of n is what we can use, is our like a data that we can use. P n plus 1 is the result that we want. So we want to modify p of n somehow to arrive at pn plus 1. So let's do this. So first we start with p of n, and we have this as fact because inductive hypothesis. Next, I will add the next term that we want, n plus 1 square, on both sides. So on the right hand side, we just add this term into, like, add it with fraction. So we times 6 to it so that we can merge everything together and have 1/6 here. And the middle term you will be able to separate it into these two, and you can see that this is in fact the formula that we want for when, so it's a formula for p of n plus 1, right? Because the last one, 2n plus t, is in fact 2 times n plus 1 and then plus 1 again. So this is the correct formula that we want. We have shown that the sum of integer square from 1 to n plus 1 equal this formula. So we have proven the inductive step, and we clear on both steps now. It means that by math induction, it is true for any positive integer n. This is the case because any positive integer, suppose k, that we want to know if the statement is true, p of k must be true, because if it's not true, p of k minus 1, the one before it, also, I will x this, also will not be true. All right, because we just proved that if the one in front of it is true, then it must be true. If we assume that for some k the statement is not true, then the one before it also must not be true. But then we can have this sequence of false statement back until we hit p of 1, right? Because positive integer, no matter how high it is, eventually this sequence will hit p of 1, and it will force p of 1 to be false, which is not the case. We just show in basic step. So this whole argument can happen. So any k that we look at, the statement must be true. And that is it for this question. Thank you.